and see how it behaves. Of course, the gravity is there, the air drag is there. And then this is a laboratory scale experiment. They have a very light friction, almost very low friction table, but still the friction, like when you deploy this, the friction of the table itself or the membrane itself will prevent it from deploying. And then the other issue is the air drag. So I'm not so sure how many of you seen that. This is done in one of the NASA centers, Glenn Research Center. It's the largest microgravity system you have here. But now what I'm going to focus is on the air drag. Now, according to Newton's law, what we learn in A levels, we know like when you drop two objects at the same time, those two should reach, or those two should move at the same rate. Right? So now what you're seeing here is a heavy ball as well as some feathers. As you can clearly see, those did not travel at the same time. Right? But the problem here is because of the air drag. Now, if you take this to a vacuum chamber, so now you don't have any air. Now you can see both of those fall at the same time. So clearly Isaac Newton was right. So this is a slow motion video. Let me wait till it finishes. So as you can see, clearly air drag plays a significant role. It didn't matter in the case of heavy ball, but of course with the feathers it mattered. So we're talking about extremely lightweight structures. So if you want to do any experiments, that plays a major role. So we're talking about microgravity or zero gravity almost. So what are the facilities available? There are different techniques. Simplest would be the gravity off-road system, where you hang things from a cable. So the tensile force in the cable will sort of offload the weight of the structure. And then what I showed you is the NASA Glenn Research Center is the largest facility available on Earth. It can reach, it can keep you 5.18 seconds zero gravity, so we have very limited time. And the height is 140 meters and diameter is only 6.1. So if you remember, the masses boom that I talked about is 20 meters in length, so it will not fit into 6.1 meter diameter. And then the other option is the reduced gravity parabolic flight. Both European Space Agency as well as NASA has that. So what happens is, in this large aircraft flies in a parabola, and for a 30-second or 28-second period you get zero gravity. And again, if you think about the size, it's 20 meters in length, 5 meters wide and 2.3 meters high. So both examples I told you, especially the masses one, will not fit into this. But of course we can do a component level or scale down structural testing. That's how we would design this. Now let me go back to the other example where I talked to you about the deployment. German Aerospace Agency's this deployable bow. So the idea here is, once you release the clamp, this should move in a straight line, so that it will apply 4 radial forces to the solar sail so that it can deploy. So now this particular structure will not deploy at all with gravity, and also friction and the air drag can prevent it too. So what you are seeing here is one of the tests that they did with parabolic flight. This is a long video, but I'll have cropped this. The first one, what you are seeing is without any control, the same structure put on a parabolic flight, European Space Agency's parabolic flight. So you can see it's coiled, and you are inside a large Airbus aeroplane. And one of them is going to hold this, and when the zero gravity is reached, they are going to release it. And the objective or the mission is to get a straight line deployment. So now the scientists are getting ready till they reach zero gravity, and once they do, you can see what we wanted is a straight line radial deployment, but clearly it's not happening. So, and if you think, actually what happens is, not only this structure fails, but this can go and hit in the other part of the spacecraft, so that can destroy the entire spacecraft. So it's extremely important that you know these behaviors beforehand. Then they tried 2 different controlling mechanisms. So I'll not show the first one, but let me go to the final one, which is basically having an uncoiling mechanism from the find, or in a way it's the carpenter tape in reverse. So you have coiled here, but in the carpenter tape everything goes inside, whereas here it will be uncoiling from the end so that it deploys in the radial, in a straight line. So we are about to reach this 30-second zero gravity, and as you can see, it deploys as a straight line. And you can see that person going and hitting his head, so scale zero gravity. Right, so these are the challenges with experiments. Air track, not having enough space or the large facilities, zero gravity, friction, and there are a lot of others. So because of these, virtual testing has become extremely important, and also the computational power develop very rapidly. It can be very useful. So most of the structures built before 2000 is being basically a trial and error process, but nowadays they are going to do a lot of compute simulations, but of course you have to verify them. So in order to verify, you need some sort of a experimental study. So let me take this opportunity to walk you through a single design case. So I'll take a case study and I'll show you different milestones and how you would reach this. So what I'm going to use is this what we call as carbon fiber reinforced polymer tube hinge. So it is, as you can see there, it's a hinge. It's the actual structure I have on my hand. So the idea here is you fold it like this, exactly what is shown in there. And then once you release the clamp, this has to deploy. Whereas in a normal one, you would have a mechanical system, a motor will rotate, and you need energy to put into this motor, and then only it deploys. The advantage here is when you are storing the energy elastically, you don't need that additional energy, just the stored energy itself will deploy the structure. Right. So this is what we are going to try to design and how you can actually fit into space, this concept, right? And also if you think about this, what I have here is two shells, curved shells. So it's actually this carpenter tape you're having two carpenter tapes. So that's the basic concept behind it. Right now, when you go into computer simulations, normal computer finite element modeling, you will have an elastic modulus and coefficient, some material parameters to be put in. But in these structures, these are carbon fiber composites that we are using. So these have different nature of material, different behavior. So you need to study the material first, what we call for multi-scale modeling. So you look at the micrograph, look at these properties, and then come up with some sort of a homogenized or effective properties into simulation. And once you can do the simulation, then you need a failure criterion to identify whether the structure has failed or not. So you have to come up with the failure criterion, and once everything is ready, if you can get all these properties correct, and if you are able to simulate, then we can think of design improvements or design optimization. So what I am going to show you is this cycle, and finally I will try to show you an example where a 2-hinge boom is wrapped around the spacecraft and whether we can design. So let me first focus on the micromechanical modeling part of it. So as I said, this has a very complex structure, but for the computer model, if you look at this tube hinge model, what we need is just some effective properties, what we call the homogenization process. So on the left hand side, you have the detailed material, and then you have to do some calculations and come up with effective properties. So the way to do it, but we look at it, so this particular material I'm talking about, what we call a plain view carbon fiber laminate. So similar to our clothes, this weave pattern is a plain weave, and then if you look at carefully, this pattern is repeating. So we take a repetitive unit cell pattern, and then we try to model it in the computer as a material model. And then you have to look at the micrograph, get these properties, the waves, cross-sectional area, waveforms, and all those things correct. And then you can simulate in the computer. We are using here the periodic boundary conditions and using the virtual work principle. I'll not go into technical details too much, but basically what you can do is go through these principles, and then you can come up with this effective property which comes as an ABD stiffness matrix, which is well known in composite structures. And then once you have that, you can see the properties you are getting, are those correct. You have to always verify what you are getting. You cannot blindly believe the computer. And then once that is ready, there's some different concepts. So what I took is only one unit cell. And then if you look at this wave pattern, so here I have two layers. So if you look carefully, like in wave theory, we talk about in phase and out of phase. So here these two are parallel. If you look at the fiber going in the longitudinal waves or parallel to the display, here it's both are going in parallel, out of phase, both are going in 180 phase difference. And then we took one unit cell here, but what about using different size of unit cell, whether there's a size effect? So all of those things you have to be carefully analyze. And then of course, as I said earlier, you have to always verify your prediction. So in this particular case, we were able to fairly well match. And then we are ready to come up with this simulation. So now in my material model, or the computer structural model, I am putting these properties here. And then I'm trying to see whether we can simulate. So the way that so what you're seeing here is the exact same which I showed you. You have two arms here rotating. So that the idea here, if you look at this, this is going to be fall rotated and then deployed. So what we need to find out is the bending moment and the torque. So this is the configuration we have here. And I'm modeling the same thing in the computer. Using the singular boundary conditions. So one of the things in this structure, probably you saw that I cannot bend it like this. If that happens, it's going to break. So I have to pinch in the middle and then only I can fall. So practically this cannot be bent like that. I'll come back to that why it happens. So then the idea is first you pinch and then you rotate and then you will achieve the 180 degree fall that we do. So what you're seeing here is the computer simulation of this. What I'm plotting here is the energy variation, and what I'm plotting here is the moment versus time curve. As you can see, the localized faulting, there's contact, so highly nonlinear geometric condition, highly nonlinear material properties as well. And then it can be folded, and then I'm going to deploy and see whether it can come back to the original configuration. So while you're looking at that, please note that there are these high peaks in moments to curves. I'll come back to that. That is an important phenomenon in these structures. So as you can see, it fully recovers back and no additional strain. So it's zero energy, and we are able to simulate it. Now, when we can do the simulations, as you can see, the stored energy is this much, so it allows us to do the calculation and see how it behaves, and then at the end, the energy becomes zero. Now, as I told you, this particular structure you cannot physically bend because it's going to break, whereas in the computer simulations you can do that. And if you can look at it, the central part here, what you're seeing here is this dark color line is while you are folding, and then the gray color line or the gray color continuous line is while you are unfolding. So as you can see here, while folding it has a very high peak. So basically if I am trying to pull it, bend it like this, it's locked into position because of the high peak. So you have to go beyond this peak in order to bend this. So that is called latching, and it's very extremely important because once the structure deployed to full configuration, if you have this latching force, it will not allow you to, it will not be flexible, it has to be stiff. So that is very important once you deploy. Then what I look at is the static configuration. Now as you see, this is a dynamic configuration, inertia based rod. So how we can analyze that? So what you are seeing here is, as I said, we are using a gravity offload system, and this is the particular hinge I showed you, and we have attached an aluminium tube to one thing to simulate another structural component, as well as this additional energy I will slow this down. So what you are seeing here is the same configuration. This same hinge is bent into 90 degrees. I have a high-speed camera directly looking at this particular hinge, and then what I am showing you right now is the real-time video with the normal camera. As you can see, this does not latch, it goes out and come back, which is not what we really want. And then if you think about the structure, at the beginning it's a symmetric structure, whereas you can see, so let me explain first. This black color object you are seeing is the actual experiment recorded through a high-speed camera, and then the green color object is the computer simulation. and I'll try to play both together. So if you carefully look after its go, we want it to stop at the straight line, but it goes the other way around. And if you look at the top one, it's folded at somewhere here, the bottom one is folded somewhere here. This is not what we need, but the positive thing is computer is able to capture it, and clearly, and once it latches, you can see a torsional motion which is not desirable in space. So we are able to capture that, which is a good thing, but then can we really do the optimization? So before that, we have to know whether the structure is failing. So we have to have a failure criterion. So there are existing failure criterion, complex criterion for fiber composites, but it does not really work in this particular case because it's a ultra thin composites. And what I'm going to present you here is we did several experiments, one the tensile test, compression test, shear test, bending test likewise, and then with that I'm not going to go into details, and it's probably the only equation I'm going to have in this presentation. But basically this failure criterion has three conditions. If this value becomes large or value becomes more than 1, that means the structure is failed. So once you have that, here I have these three equations. Here I call them Fy1, this failure index 1, 2 and 3. This is basically axial dominated, this is bending dominated, this is coupling axial and bending coupling. So the simulation predicted that it's going to crack at this location, and we did an actual test and it's actually cracked at the same location. So now we are confident about our simulations as well as failure criteria, and then that allows us to go into design improvements. So going along the same hinge, if you remember what I presented at the beginning, this particular structure, they did only experimental studies, trial and error process, and they came up with this particular hinge configuration. They didn't do any simulations on this level, no high fidelity simulation. So we use this as a basic structural arrangement. We parameterize it using slot length and the encircle diameter, and then we try to play around it varying these parameters. Now, if you remember this masses booms, as I said, first they flatten this, then rotate and fold it. So if I show you the simulation, you can see first we are flattening it to half the diameter of the tube. And then you can fold it and achieve what you want. So and then we have a failure criteria and see whether it's failing or not. So when you do this, as I said, first we tried and it said it's failing, and we modeled built that as well, and we found out it's failing, and then we came up with the selected slot length of these parameters, and it worked, and we actually built it and found out it can be folded as well. Now then, once you have that, let me try to explain the final step where we can actually use this in an actual structural configuration. So the idea here is you have a 1 meter long boom wrapped around the spacecraft, rigidly connected to it, and one condition is once this deploy, it has to fully latch. It should not go beyond this point. If you remember the previous hinge, it actually went in, which is undesirable, but we call overshooting. There should not be any overshoot. So now this is an example of overshooting. So I have this spacecraft here wrapped around. It starts deploying from this point. You can see clearly initially only this hinge rotates, not the other one. So it's important to know how it behaves. And then after that, but we have to stop it here, but it actually went out. So then we did further improvement to the design, and finally we came up with the design where it's fully lapsed. So now the next step is computer said this be true or whether it will work. So we did an experiment. I'm not going to go into details too much, but what you're seeing here is the real-time video, and this will be the high-speed video as I shown you earlier with the different hinge. So as you can see, this rapidly deploys and it does not overshoot, and this is a slow-motion video taken through a high-speed camera. So hopefully I hope that you got an idea about the overall design process of a deployable boom. So now this actually is a project later on happened with the Caltech, University of Surrey and Jet Propulsion Laboratory, NASA Jet Propulsion Laboratory. Here the mission is that they have 4 what you call CubeSats, small satellites. These 4 can separate and fly with respect to each other. So the idea is that there are some mirrors where we focus on the certain, let's say, a star or something. So depending on the configuration, you can change the focal length. So if you look at the middle part of it, these are arranged in a box type of structure, whereas this is more in a linear. So you need a camera further away from this so that you can observe the position of these, and then they can talk to each other and reposition. So in order to get this camera, it has to attach to something. So the idea, they came up with a similar hinge, a similar boom with it had 4 slots, and then they can. So it's actually being used right now. And then I'll show you one final example with related to this. This is Caltech Space Solar Power Project, state of the art. I'll go through details. But the idea here is basically you're talking about the space solar power. If you are on Earth, you get cloud cover, rain, and day and night. All those things are going to affect you. Whereas if you have your solar sails in space, you get almost unlimited power. Of course, depending on the location, the positioning. And then if you have a system where you can wirelessly transfer that energy onto Earth, that will be definitely an advantage. One is the efficiency, other one is the location. Now, you cannot have cables. The earlier system, this concept has been there from 1940s. But the problem is they have been thinking of using X-rays, which basically evaporate anything coming through that, whether it's an aeroplane or a bird. But now they are going into radio frequencies and trying to see whether they can be done. That is one challenge. And then the other thing is, I'll play the video, then it will be much more clear. You have photovoltaics, and then the backing structure is the structural component, and then also a frequency, a signal processing, where you direct this power. That's more sort of electronics. So the 3 professors at Caltech, one from electronics, one from materials, and my supervisor who's from structures, are developing this. So they actually sent this to space in December, and now they are trying. Right? So the idea here is you will have several satellites, one of these block, and then this is the moonflower that I talked to you about. The concept here is the moonflower. And these are laboratory scale experiments. So this is the structural components, but then you have the photovoltaics, structural stiffness, as well as the RF layer. So there are 3 layers. So this is a true multidisciplinary project where you have to bring all 3 together, and they were able to do it in a single layer. Structural stiffness, electronics, as well as communications. And so what we call is a tile. This will be combining several, and what the unit you saw is this one. And then there will be several of these spacecraft flying around Earth. And then if they can channel the energy to the correct place they want, it can be even middle of Africa, the desert, or during war as well. So what you're seeing here is the actual experiment, laboratory scale experiment. What you're seeing here is the tile, and this is the receiver. As you can see, when you put your hand, it's going to block. So this wireless power is already there, commercially available, but the idea here is it's put it into space, and whether you can transfer it through space at a long distance and location. So it's actually being tested right now in space as well. So with that, I'll just quickly go through a couple of other sites that I am going to working on. So with regard to the same thing, now one of the problems is, here you can see, if you look at these structures, it's curved highly. Whether you can break that. I mean, this particular material will break at a certain curvature. Whereas, so that's a limitation in compaction. And then also we are looking at, our model was initially non-linear linear model. Now we are trying to see whether we can capture the non-linear part. And then this is another example where you use 2 different materials. This is the silicon, where it allows you to go into a very small country, almost 180-degree fall, and it will not break. And then coilable booms, what is used in space structures, that example I showed you. There are different, I will not go into detail. So this is the exact Caltech solar power project they are using this. And then if you think about these rooms, it's an example where NASA is planning to use high-level rooms in, let's say, a moon habitat or a Mars habitat. So you can come up with all these as the deployable structures. This is lightweight as well as you have to erect rapidly. So if you make out of this steel, it can be used even on Earth. And also depending on the type of configuration and the stiffness, it can be permanent or temporary. And then I did not talk about the membrane structure. There are a lot of work going on in that area. The membrane wrinkling as well as crease locations, all those things are important. So with that, I would like to acknowledge the funding agencies, the Enrich Common Trust, California Institute of Technology, National Research Council, National Research Foundation Sri Lanka, in the Sri Lanka Joint Research Program, University of Colorado, of course, and Ceylon Steel Corporation. Thank you very much.
Thank you, Professor Chinthaka. That's captivating. Yes, I think you did real justice to our inaugural lecture, and maybe we should look forward to doing structural engineering. Right, may I invite Professor Tilaka to hand over to our conversation for our person. Thank you. That brings to the end, but let me just take a minute in acknowledging our sponsors to have the inaugural lecture at University of Colorado. Cargill's as the event sponsor, Daily FT as the print media sponsor. We carry on the news in the print media. And of course, Sri Lankan Scientist as a social media sponsor. So the only Sri Lankan science magazine they carry. Thank you very much, and thank you all for coming and joining for this wonderful lecture. And till we meet again, goodbye.